There is a single symbol in physics that refuses to behave. It was invented to solve a mathematical problem, discarded as an embarrassing failure, and it has now returned as a force that violates our laws of physics, the cosmological constant, lambda. In 1917, Albert Einstein hit a wall. His newly published equations of general relativity predicted that a universe held together by gravity would eventually collapse inward on itself. To force the math to match his belief in a static, unmoving universe, he added a fudge factor. He introduced lambda to represent an outward push that perfectly countered the pull of gravity. This constant existed solely to achieve a state of total stillness, preventing the cosmos from either expanding or shrinking. But in 1929, Edwin Hubble proved the universe was expanding. Einstein's static model was physically impossible. Einstein scrubbed the constant from his equations, allegedly calling it his biggest blunder. For the next 50 years, the scientific community assumed its value was exactly zero. The foundational consensus of 20th century cosmology rested on the total absence of this force, treating Einstein's balancing act as a historical embarrassment. In 1998, astrophysicists studying distant supernovae realized that the universe's expansion was speeding up. Gravity should have been slowing the expansion down. To account for galaxies accelerating away from each other, physicists brought Einstein's blunder back to life. We now call this resurrected force dark energy. Based on current measurements, it makes up 68% of the entire mass energy budget of the cosmos. To understand the mechanism behind this push, we have to look to quantum field theory. Down at the smallest scales, empty space is never a total void. Virtual particles are constantly popping in and out of existence, creating a vacuum energy that pushes space outward. This matches Einstein's exact cosmological constant. While cosmologists needed a theoretical placeholder for cosmic acceleration, quantum mechanics provided the physical engine. Einstein's abandoned constant was real, and it was dictating the expansion of space. But when quantum physicists calculated how much vacuum energy should exist, the mathematics failed. This chart compares what we see through a telescope with what we calculate on a notepad. The actual amount of energy measured in the night sky is almost zero. The quantum prediction exceeds that observed value by 120 orders of magnitude. This discrepancy is widely cited by physicists as the worst theoretical prediction in the history of science. Our two most successful frameworks, quantum mechanics and general relativity, are embarrassingly incompatible when it comes to measuring the single most dominant force in the universe. This isn't just an abstract math problem. Because we cannot agree on the true value of this number, we cannot predict how the universe will die. If the constant remains exactly steady, the big freeze occurs. Galaxies will drift apart, stars will burn out, and reality will go cold and dark. If the constant is actually a decaying field that loses its strength over time, gravity wins the tug-of-war. The universe will eventually pull itself back into a singular collapse called the Big Crunch. If dark energy grows exponentially stronger, it will overpower gravity entirely, tearing apart galaxies, solar systems, and eventually atoms themselves, the Big Rip. Recent data from modern surveys suggests a new possibility. The cosmological constant might not be constant at all. It may be evolving. An evolving dark energy elevates the Big Rip and the Big Crunch from mathematical oddities to plausible futures. Einstein's biggest blunder wasn't just a historical footnote. It is the active, shifting executioner that will ultimately decide how everything we know will end.